Welcome to Talk Tensors.
Glad to be here for this one.
Yes, so bring your mind all the way back to the year 2017.
Oh, wow. A lifetime ago in machine learning years.
Right. I mean, the deep learning boom is in absolute full swing.
Oh, yeah.
The air in every computer science department is just buzzing with this arms race to build deeper, more massive convolutional neural networks.
Yeah, everyone was obsessed with architectures like ResNets and VGGs.
Exactly. These monolithic digital brains that require, billions of floating point operations.
Massive, dense matrix multiplications just to make a single forward pass.
Right. And, well, if you have a data center, if you have a rack of GPUs plugged into some industrial cooling system, that paradigm is perfectly fine.
Sure, you don't care about efficiency as much there.
But I want you to imagine taking one of those power-hungry, parameter-heavy architectures and trying to run it on, say, a commercial drone.
Right, or like a battery-powered robot vacuum.
Exactly, or an off-the-shelf smartphone from that era.
Oh, your battery just drains in minutes.
Yeah, assuming the mobile sock doesn't thermally throttle into oblivion first, right?
Yeah, exactly. And that was the thing. The field was experiencing this profound hardware-software mismatch.
Mm-hmm.
The algorithmic capabilities were unprecedented, but they were entirely landlocked to server farms.
Right, you couldn't untether them.
Exactly. So the engineering mandate shifted rapidly toward untethering these models.
So what was the actual goal then?
The goal became achieving state-of-the-art visual recognition on edge devices.
Okay.
Devices with highly constrained computational budgets. Specifically, we're talking about operating within this brutally tight window of 10 to 150 MFLOPs.
Wow, 10 to 150. That is tiny compared to a ResNet.
It's basically nothing.
So that brings us to the mission of our deep dive today. We are examining an architecture that basically abandoned the trend of simply scaling up parameters.
Right.
And instead, they fundamentally restructured how information flows through a network.
Yeah, it was a totally different approach.
So if I had to give a one-sentence thesis for this paper, it would be this. By introducing a brilliant channel shuffle operation paired with pointwise group convolutions, this design broke the efficiency bottleneck.
It really did.
It allowed mobile networks to maintain wide feature maps without just completely overwhelming the processor.
Right. And for the roadmap today, we're going to unpack the exact state of the field prior to this work. We'll break down the specific methodology and architecture, block by block.
Awesome.
Then we'll analyze the empirical results that honestly left competing models in the dust.
And of course, we'll finish up with our novel notions segment.
Yes, pitching some wild new research ideas based on this paper's legacy.
Exactly. So let's get into it. The bottleneck and the bottleneck, the pre-ShuffleNet era.
Right. So the conventional wisdom for deploying to mobile before this shift was, it was an incredibly brute force.
Yeah, totally.
Teams would take a massive proven network and just subject it to really aggressive pruning or quantization.
It's they were essentially taking a sprawling mansion and trying to forcefully compress it into a studio apartment.
That is a perfect way to put it. You can cut away connections or, use low bit precision to round off the weights.
Right.
But you're still fighting the innate topology of a model that was just never meant to be efficient.
Which naturally led to the rise of custom-built mobile architectures.
Right. Exactly. We saw models like SqueezeNet significantly reducing parameter counts using their Fire module.
Oh yeah, SqueezeNet was huge.
And contemporaneously, you had MobileNet and Exception emerging.
Right, and they popularized depth-wise separable convolutions.
Which was a massive leap forward in computational efficiency. They decoupled spatial filtering from channel mixing.
Right. But even with depth-wise convolutions handling the spatial dimensions, the premier architectures of the time, like ResNeXt, carried this fatal flaw when you tried to scale them down at ultra-low compute budgets.
Yeah, they really did.
And that flaw was the dense one-by-one convolution.
The math behind that fatal flaw is actually pretty simple to understand.
Break it down for us.
So the one-by-one pointwise convolution is basically the mechanism the network uses to mix information across different channels.
Okay.
In the ResNeXt topology, the designers optimized the heavier 3x3 spatial convolutions by using group convolutions.
Right, partitioning the channels into discrete groups to lower the MAs, the multiply accumulate operations.
Exactly. But they left the one-by-one layers completely dense.
Meaning every single input channel projected to every single output channel.
Yes. And the mathematical overhead of that dense projection is staggering.
Just how staggering are we talking?
Well, in a standard ResNeXt residual unit, those one-by-one pointwise layers devour 93.4% of the total multiplication adds.
Wait, 93.4%?
Yeah, almost 94% of the silicon's clock cycles are being spent on this one specific operation.
That is wild.
It is. And when you're operating under a strict, say, 40 MFLOPs budget,
Right?
an expensive, dense one-by-one operation taking up 93% of your compute forces a devastating architectural compromise.
You have to drastically reduce the dimensionality of your feature map.
Exactly. You basically starve the network.
Right, because thinner networks with fewer channels inherently lack the manifold capacity to encode rich, complex representations.
Yeah, the accuracy just drops off a cliff.
Okay, let's unpack this with an analogy. It's like an incredibly expensive toll booth on a highway.
I like that.
Every single piece of data, every tensor, has to pay a massive computational fee to cross this dense one-by-one layer. And if your hardware budget only allows for a few dollars, you can only afford to send a trickle of data down the highway.
Right.
So the obvious countermeasure to this toll booth would be to just apply the same group convolution trick to the one-by-one layers that ResNeXt applied to the 3x3 layers.
Right, that's the logical next step.
You partition the channels, drop the FLOPs, and bypass the toll booth entirely.
And yes, partitioning the one-by-one layer immediately solves the FLOP constraint.
What?
But it introduces a severe critical side effect in the network's forward pass.
Okay, what is it?
We can define it as a catastrophic lack of crosstalk.
No crosstalk.
Right. When you stack group convolutions, you're basically forcing the feature maps into isolated silos.
Okay, walk us through the mechanics of that.
Sure. Assume you partition your input channels into 3 distinct groups. Let's say Group A, Group B, and Group C.
Got it.
The convolutional filters assign to Group A compute a representation strictly derived from Group A's input.
Meaning the output channels generated by Group A are exclusively a function of Group A.
Exactly.
And when that tensor flows into the next layer, which is also group convoluted.
The filters for Group A are once again only looking at the siloed output from the previous step.
Right. So the receptive field across the channel dimension is completely severed.
Completely blocked. The representations in Group A never interact with the representations in Group B or C.
And neural networks really rely on hierarchical feature synthesis to resolve complex patterns, don't they?
They absolutely do. If Group A learns, say, edge gradients, and Group B learns texture frequencies, the network requires a dense projection to fuse those primitive features into a higher order concept.
Like a semantic object boundary.
Exactly. But by stacking group convolutions, you trap those primitives in their respective partitions.
So the loss landscape becomes highly suboptimal because the gradient can't flow across the channel groups to learn joint representations.
Exactly. Information flow between channel groups is just totally cut off. The representation capability is severely weakened.
All right, so here is where it gets really interesting. This is the core breakthrough.
Yep.
The genius solution, which is the paper's namesake. The channel shuffle.
It's such an elegant fix.
The channel shuffle operation directly attacks this isolation. The architecture basically requires the data from these disparate groups to mathematically interleave before passing into the subsequent layer.
Right. And the mechanism for doing this without introducing new trainable parameters or heavy matrix multiplications is incredibly smart.
Walk us through the exact mechanism. Keep it in plain language for us.
Okay, so if your grouped convolutional layer outputs a tensor with G groups, and each group has N channels, you take that output dimension and reshake it.
Reshape it into what?
Into a 2D matrix of dimensions G by N.
Okay, so the rows represent the isolated groups, and the columns represent the individual channels within those groups.
Precisely. Then you just apply a mathematical transpose.
Meaning you swap the dimensions to N by G.
Yes. And finally, you flatten the tensor back out into a contiguous 1D sequence of channels for the next layer.
Okay, I've got another analogy for this. It's like organizing a massive corporate networking event.
Oh, I like where this is going.
You have this huge banquet hall where everyone is seated by department. Engineering is at one table, marketing at another, accounting at a third.
And that seating arrangement is the stacked group convolution.
Exactly. They spend the entire epoch talking among themselves, and absolutely no interdepartmental synergy occurs. No big idea spread. But the reshape and transpose operation is simply ringing a bell and forcing one person from every table to move to a newly formed table.
Right, you're dealing the deck of cards.
Yeah. You flatten the room back out, and instantly, every new table has an engineer, a marketer, and an accountant. Suddenly, the whole room is cross-pollinating ideas.
That is perfectly stated. And the operational brilliance of that reshape, transpose, and flatten sequence is that it's entirely differentiable.
Wait, really? Just reshaping the matrix is differentiable?
Yes. The computation graph remains totally intact. During the backward pass, the autograd engine can perfectly track that permutation matrix.
Wow.
So it allows the error gradients to route back to their originating filters. The network still learns end-to-end via backpropagation without the shuffle breaking the chain.
That is so clean. And this topological routing works regardless of whether the consecutive convolutional layers have identical group numbers, right?
Exactly. It's incredibly robust.
Okay, so taking this theoretical mechanism and mapping it onto a physical architectural block, let's dissect the architecture component by component.
Let's do it.
We can basically trace the exact life cycle of a tensor moving through the ShuffleNet unit.
Right. The authors start with the topological skeleton of a classic ResNeXt bottleneck block.
But they systematically gut the computationally heavy components.
Yes. Step 1 is entirely replacing the initial dense 1-by-1 convolution.
Okay, so what do they put in its place?
They instantiate their new pointwise group convolution.
Right.
And that's followed immediately by the channel shuffle.
Got it. So they shrink the channel dimension, but they maintain that cross-group representation we just talked about.
Exactly. Then the tensor, which is now mathematically mixed and bottlenecked, flows into step 2, the spatial processing phase.
And this is where they utilize a 3x3 depthwise convolution, right?
Yes, because depthwise operations are intrinsically cheap. They apply a single spatial filter per channel, so they avoid that dense cross-channel summation entirely.
That makes sense.
Yeah.
But there's a really subtle detail here. They actually omit the nonlinear activation function after this specific depthwise layer.
Yes, no real U activation there.
Why is that? In a standard block, a real U activation follows almost every convolution to inject nonlinearity.
Right, but applying a standard real U to a heavily bottlenecked feature map actually induces manifold collapse.
Oh, wow.
Yeah, if your channel depth is severely constrained, zeroing out all the negative pre-activations disproportionately destroys the learned representation.
So leaving the depthwise output linear preserves the fragile variance of the tensor.
Exactly. You don't want to destroy data when you have so little of it to begin with.
Makes total sense. Okay, so after the spatial filtering, step 3, the tensor hits the final phase of the block.
The expansion phase. Here they finish with a second pointwise group convolution.
And this projects the channel dimension back to its original width, so it matches the shortcut path.
Correct. And notably, they explicitly omitted a second channel shuffle here.
No shuffle needed on the way out.
No, empirical testing showed that adding an additional shuffle at the end of the block yielded diminishing returns.
Oh, okay.
The slight boost in accuracy just didn't justify the minor memory bandwidth overhead.
So the expanded tensor is added to the shortcut tensor, a final real U is applied, and the unit is complete.
That's the ShuffleNet unit.
Okay, so let's talk about the math of the efficiency here, because this is where the rubber meets the road.
Oh. The algebraic equations for the computational complexity are beautiful. They really prove why this arrangement dominates the FLOP constraint.
Give the listener the equation context.
All right, so given an input feature map with a spatial resolution of, say, H by W, with C input channels and a bottleneck dimension of M channels, a standard ResNet block demands FLOPs proportional to HW times 2 centimeter plus 9 meter squared.
Right. And the ResNeXt optimization alters that to HW times 2 centimeter plus 9 meter squared divided by G.
Exactly. The 3x3 component is divided by the group size G, but the 2 centimeter term,
representing those dense 1-by-1 layers.
Right, that remains a massive unscaled penalty.
So what does the ShuffleNet block's complexity equation look like?
The FLOPs plummet to HW times 2 centimeters divided by G plus 9 meter.
Wait, so the 2 centimeter bottleneck term is now directly divided by the group parameter G.
Yes. The magnitude of this optimization cannot be overstated for mobile silicon.
I mean, if you constrain the architecture to a hard ceiling of 40 MFLOPs,
right,
dividing the pointwise compute by a factor of 4 or 8 allows you to just proportionally expand the channel width of the network.
Exactly. You get to use incredibly wide feature maps while remaining perfectly under the thermal and computational limits of the hardware.
And wider feature maps mean more information encoded, which is basically the lifeblood of tiny networks.
It is. The network gets wider, the manifold capacity increases, and the representations just become richer.
Okay, but what about when the spatial dimensions of an image need to downsample? Like as the tensor propagates deeper into the network?
Right, the stride 2 variation.
Exactly. How does the unit adapt when the spatial size needs to shrink?
When the architecture dictates a stride of 2 to have the spatial resolution, the unit undergoes 2 specific topological shifts.
Okay, what's the first one?
First, they add a 3x3 average pooling layer on the residual shortcut path.
With a stride of 2, obviously, to match the spatial downsampling of the main branch.
Exactly. The second modification occurs at the summation node. Instead of performing an element-wise addition between the main branch and the shortcut path, the architecture executes a channel concatenation.
Oh, concatenation instead of addition. Why is that brilliant?
It's highly strategic. When a network halves the spatial resolution, standard architectural practice dictates that you double the channel depth to preserve the representational bandwidth.
Right, you trade spatial resolution for channel depth.
Exactly. So by concatenating the shortcut tensor onto the main tensor, you effortlessly enlarge the channel dimension.
Oh, wow.
And you do it with almost 0 extra computational cost. No multiply accumulate operations needed.
That is so smart. Okay, I'm going to push back here for a second, though.
Go for it.
So what does this all mean for the actual physical hardware? Like, the depth-wise convolution looks great on paper, but why did the authors isolate it strictly to the bottleneck feature maps?
That is a crucial realization the authors made about real-world hardware.
Because relying on depth-wise convolutions heavily introduces a secondary constraint, right?
Yes. Depth-wise operations have incredibly low theoretical complexity. In the equation, they look like a rounding error.
Right.
But practically on low-power mobile devices, particularly the ARM architectures prevalent in 2017, they have a terrible computation-to-memory access ratio.
Ah, so the architecture becomes entirely memory-bound rather than compute-bound.
Exactly, because a depth-wise convolution applies a unique filter to every single channel independently.
Right.
The processor cannot utilize highly optimized, dense matrix multiplication routines like Bailey or GMM.
So the arithmetic logic unit basically just sits idle while the memory controller continuously fetches small fragmented chunks of data from the L1 or L2 cache.
Yes, the memory bandwidth and bottlenecks the entire forward pass. It creates a crippling overhead.
It's the equivalent of a Michelin star chef who chops vegetables at lightning speed.
Okay.
But stores every single carrot and onion in a different refrigerator across the building.
That's hilarious, but exactly right.
The chef's theoretical throughput is massive, but the actual output is gated by the time spent running back and forth.
Precisely. So by intentionally sandwiching the depth-wise convolution between the two grouped one-by-one layers,
they drastically reduce the channel depth before the spatial filtering occurs.
Yes, they deliberately bottlenecked it. It corrals the necessary data into a smaller memory footprint, minimizing the cache misses and keeping the processor fed.
Wow. So they weren't just optimizing equations on a whiteboard?
No, not at all.
They were architecting around the physical memory hierarchies of mobile system on chips.
It's a really deep understanding of physical silicon execution.
So let's look at the empirical evidence. Section 4. Benchmarking the beast. Did this actually work in practice?
Oh, it worked beautifully. We see the validation of this hardware-aware approach in the benchmarks.
Let's set the stage. What was the benchmark?
They evaluated against the ImageNet 2012 classification dataset.
Okay, the classic. And who was the reigning champion of mobile vision at the time?
That would be MobileNet. MobileNet heavily utilized depth-wise separable convolutions, but it lacked the grouped point-wise optimizations we've been talking about.
Right. So what was the showdown result? Deliver the knockout stat for us.
All right, at the extreme low end of the compute spectrum, strictly enforcing roughly a 40 MFLOPs constraint, the ShuffleNet architecture achieved an absolute 7.8% lower top one error than MobileNet.
7.8% lower error.
Yes. In the context of ImageNet evaluations, a 7.8% absolute reduction is a generational leap.
That is incredible. And did that hold up as the models got bigger?
It did. It outperformed MobileNet across all complexity levels, consistently demonstrating superior representational power per arithmetic operation, even up to 500 plus MFLOPs.
Okay, but how do we know that channel shuffle was the specific secret sauce? Let's talk ablation studies.
Right, the rigorous controlled experiments proving the hypothesis. Table 3 in the paper asks, what happens if you remove the shuffle?
And what happened?
They compared identical networks trained with and without the channel shuffle operation.
Okay.
The results showed that the channel shuffle consistently boosts scores across the board.
How big of a boost?
Well, it gets more pronounced as the number of groups increases, with a larger group number like G equals 8.
For the input channels are fractured into 8 isolated silos.
Exactly. In that scenario, the model with the shuffle outperforms the no-shuffle version by a massive 5.8%.
Wow. Because a higher group number induces a more severe no crosstalk penalty.
Right. The isolated feature maps aggressively overfit to their local partitions if you don't shuffle.
So cross-group information interchange is undeniably essential.
Absolutely. The shuffle operation is the only topological bridge allowing the gradient to optimize global representations.
And what about the group size itself? What did Table 2 show?
Table 2 revealed a fascinating dynamic for ultra-low compute budgets.
Okay.
Smaller models actually benefit more from larger group numbers.
Really? Why is that?
Because the tightest FLOP constraints force the most aggressive bottlenecks. If you use a small group number, you can only afford a very narrow feature map.
Right.
But by pushing the group number up to 8, you fracture the computation, allowing for a dramatically wider feature map under the exact same MC ceiling.
Ah, I get it. So the network trades dense interconnectivity for sheer channel volume.
Exactly. And it relies entirely on the deterministic shuffle to fuse those high-dimensional, hyper-specialized features.
It's like when you have a tiny budget for a startup.
Here we go.
You can't afford a huge generalist staff.
Right.
The dense one-by-one generalists are just too expensive.
Right.
So instead, you rely heavily on hyper-specialized freelancers, large group numbers. One writes code, one designs graphics, one manages SEO. They operate in complete isolation. But to keep the company, the feature map, broad and capable, you rely on the central architecture, the shuffle operation, to routinely force these contractors to synchronize their outputs.
Exactly. And the broader organization functions with much higher capacity than a tiny team of generalists ever could.
That makes perfect sense. So was this just an ImageNet one-trick pony?
Not at all. The transfer learning capabilities proved that these hyper-specialized features were not merely overfitted to ImageNet.
So they look beyond classification.
Yes, they did MS COCO object detection tests using the faster RCNN framework.
And object detection is notoriously hard, right?
Yeah.
It requires high-resolution spatial reasoning.
And complex multi-scale feature synthesis. But at a 600-pixel resolution, ShuffleNet achieved a superior MAP, or mean average precision, over the MobileNet backbone.
What were the numbers?
It hit 25.0% MAP versus MobileNet's 19.8%.
That's a huge jump.
It proved generalizable transfer learning. The backbone was incredibly robust.
All right, so section 5, rubber meets the road. Actual speed up and lasting impact.
This is where we talk about hardware again.
Because theoretical math doesn't always translate to the real world.
Yeah, it is true.
Theoretical metrics like MAP and MFLOPs dictate the academic narrative, but physical inference latency is what dictates real-world utility.
Exactly. Theoretical FLOP reduction is notoriously decoupled from physical clock cycles.
So what happened when they actually put this on a phone?
They profiled the actual latency on an off-the-shelf ARMM-based mobile device, specifically a device featuring a single Qualcomm Snapdragon 820 processor.
Okay, a very standard mobile chip for the time. What were the results?
It achieved a roughly 13x actual inference speedup over an AlexNet baseline while maintaining comparable accuracy.
13x speedup. That's fantastic. But wait, what was the theoretical speedup supposed to be?
The theoretical FLOP calculation projected an 18x reduction in complexity.
Oh, so theoretical was 18x, but actual was 13x. Why the drop?
The discrepancy is entirely accounted for by memory access latency and other overheads.
Right, because moving pointers in memory, reading and writing fragmented tensors.
And executing the transpose operation within the shuffle itself. All of that consumes clock cycles without registering as a FLOP.
So the authors transparently quantified this decay.
They did. They noted that every 4x reduction in theoretical MACE yielded about a 2.6x actual speedup on the Snapdragon silicon.
Okay, so there's a serious friction there. And that friction was highlighted even more in the squeeze and excitation, or SE blocks experiment, right?
Yes, the SE cautionary tale. This is a crucial lesson.
Tell us about it.
So SE blocks introduce a state-of-the-art channel-wise attention mechanism.
Okay.
They execute a global average pooling operation over the spatial dimensions, followed by a tiny, fully connected bottleneck to learn channel weights.
And from a pure FLOP perspective, adding SE blocks to the network is practically free, right?
Exactly. The theoretical compute overhead is a fraction of a percent.
And did it help the accuracy?
Oh, it behaved exactly as the literature suggested. It boosted accuracy nicely, dropping down to a 24.7% error for the 2x scaled model.
Nice.
But when they deployed that SE-equipped model onto the physical Snapdragon 820 chip, it made the network 25% to 40% slower on the mobile device.
Wow. 25 to 40% slower, despite having a negligible theoretical complexity increase.
Yes, because the SE block requires a global average pool.
Meaning the memory controller must sweep across the entire spatial footprint of the tensor just to compute a single scalar per channel.
Exactly. And this operation aggressively evicts data from the processor's L1 cache.
Oh.
The subsequent tiny, fully corrected layers are highly memory bound. The architecture was basically just waiting for data to arrive from RAM rather than performing mathematics.
So the core lesson here is that actual inference speed evaluation is critical.
You absolutely cannot design low-cost architectures purely on paper. You have to take a holistic view of the silicon's memory hierarchy.
So how would you summarize the lasting influence of this paper?
I'd say this paper fundamentally altered mobile architecture design. It proved that how you route data, like shuffling it, is just as important as how you compute it.
You can maintain representational capacity by meticulously managing how the tensors interleave, rather than relying on brute force matrix multiplication to find correlations.
Exactly. It forced the transition from pure FLO key counting to hardware-aware topological design.
Incredible. And that legacy leads us perfectly into our final segment, Novel Notions.
I love this segment.
It's time for Novel Notions, where we take the legacy of this paper and pitch an outlandish but technically plausible new research idea.
Let's hear it.
And as always, a quick disclaimer. This is for entertainment purposes only. Do not base your PhD thesis solely on what we're about to say.
Please don't. I'll initiate the first notion.
Go for it.
So the core problem solved by the channel shuffle was the no crosstalk isolation caused by grouping computations to save FLOPs, right?
Right.
What if we map that identical constraint onto the current era of edge computing?
Okay. So instead of spatial CNNs, you're talking about large language model.
Exactly. Running LLMs natively on edge devices. Let's explore dynamic temporal shuffling in edge LLMs.
Oh, I like the sound of that. What's the pitch?
The bottleneck in edge LLMs is the dense projection of the hidden dimension within the multi-head attention blocks.
Right. Current transformers use massive, dense linear layers to project queries, keys, and values.
And if you're operating on a low-memory mobile SO, those dense linear layers consume gigabytes of bandwidth.
So how do we fix it using this paper's logic?
You replace those dense projections with grouped linear layers. You strictly silo the attention heads to save compute.
Meaning head 1 only projects and attends to a specific subpartition of the hidden dimension.
Exactly, and head 2 operates on a completely separate partition.
Okay, so you instantly bypass the massive compute cost of the dense projection.
Right.
But wait, siloing the attention heads in a language model guarantees semantic collapse.
It does.
Because if head 1 tracks syntactic structure and head 2 tracks semantic sentiment, keeping them partitioned means the model cannot synthesize the grammar with the tone.
Exactly. To prevent that no crosstalk between semantic concepts, you apply a deterministic token-level channel shuffle between transformer blocks.
Oh, wow. So before the token embeddings hit the layer normalization of the next block, you apply the reshape, transpose, and flatten sequence to the hidden dimension of every single token.
Yes. You physically permute the hidden states. The semantic features learned by head 1 are mathematically interleaved with the syntactic features of head 2.
So the subsequent grouped attention heads receive a completely cross-pollinated tensor.
Exactly. This could theoretically allow tiny on-device LLMs to maintain a wide hidden dimension, which is crucial for complex reasoning without the exponential compute cost of dense matrix multiplications.
You are shuffling contextual routing instead of spatial feature channels. That is brilliant.
And because the reshape and transpose are standard memory operations, the computational overhead is negligible.
Okay, I've got a counterpitch. Novel notion number 2.
Let's hear it.
I'm going to focus entirely on the physical silicon gap we talked about.
The gap between theoretical and actual speedup.
Exactly. We noted that the theoretical 18x speedup decayed to a 13x physical speedup because the fixed shuffle operation caused memory access overhead.
Right. The matrix transpose forces the processor to read and write uncoalesced memory blocks.
So let's propose hardware-aware evolving shuffles utilizing neural architecture search, or NAS.
Hardware-aware evolving shuffles. Okay, what's the mechanism?
Well, the original paper uses a uniform static shuffle operation. It blindly maps row I to column J.
Right, without knowing if column J is currently residing in the L1 cache, the L2 cache, or all the way out in DRAM.
Exactly. What if the shuffle pattern itself became a learned, highly irregular parameter dictated by NAS?
Okay.
Instead of a perfect reshape and transpose, the network learns a sparse routing matrix that shuffles channels specifically based on the L1, L2 cache size of the deployment hardware.
Oh, wow. Like optimizing specifically for an Apple Watch chip or an IoT sensor?
Yes. You profile the exact target hardware. The NAS algorithm evaluates thousands of different permutation matrices, measuring the physical cache miss rate of each one.
So the objective function isn't just accuracy, it is memory continuity.
Exactly. It learns a routing pattern that perfectly aligns the shuffled channels with the physical memory banks of that specific silicon die.
So it groups the interleave channels adjacently in memory so the processor can execute burst reads.
Yes. It would squeeze out that remaining gap between theoretical speedup and actual speedup by ensuring the channel shuffle bypasses the memory overhead entirely.
You're merging compiler optimization with topological design.
Exactly. Evolving a custom data flow pattern optimized for the specific thermal and cache constraints of its environment.
Both of these extrapolations just validate the enduring relevance of the paper's core thesis. Efficient inference is rarely about raw processing power. It is almost entirely an exercise in intelligent, deterministic data routing.
And that structural elegance is what makes this architecture a fundamental pillar of modern edge computing.
It really is.
So next time you use a facial recognition feature or a smart camera on your phone without draining your battery in 10 minutes, remember the unseen traffic cop inside the silicon, constantly shuffling data to keep the whole system moving.
Well said.
Thank you for joining us on this deep dive on Talk Tensors. Keep learning, keep questioning, and we will see you next time.